There we go. Okay, so what should we do with those three missing neighbors that we have at the corner? And it can get worse, right? If you are considering not this neighbor, but this neighbor right here, it only has, well, three other neighbors. So we are missing five other neighbors. So the rules of game of life like can't apply to this particular neighbor. So what should we do to this particular cell? So what should we do? What do you think? Okay, Joshua says, have it set to a random state each time you update it. That is definitely a good solution. We could even try it. We could even try to implement it. So I would be hesitant as to whether or not it creates some random noise in the corners that could disrupt the entire system. Because depending on the probability that you give each of these cells at the beginning of your game, you know, you can really explode the population density and kill all of the other cells in the center. But it's a good idea. Okay, Justin, do you have an idea that you'd like to share with us, or would you like me to keep going? Let's wait a little bit for Justin. Okay, but definitely, Joshua, that was a good idea. So initialize the cells in the corners to a random state. Okay, so let's keep moving. So, you know, this is a problem that you're going to encounter often when you are programming something is, you know, there is this object that has to communicate with its surroundings, particularly in a list, right? So you have a list and you are in a particular index. So you can be the element 0. And the element 0 contains, you know, if you want to make reference to the object to the right is your current index plus 1, right? Or in other words, let's say that you have a list like this. Oh, I see the answer. Imagine a 50 by 50 in every non-existent neighbor. Okay, so also like initializing with a 50-50 chance of being alive in every non-existing neighbor. Oh, okay, I see what you mean, like simulating it. Got it. Okay, so if you have a list of elements, list A, for example, is going to be equal to, I don't know, 1, 2, 3, etc. Okay, it's a list of integer values. So the first index, if I want to refer to my first index, I'm going to say list of A 0 equals, well, equals 1 is this element right here. So if I wanted to refer to the second item relative to the first one, what I could do is say, hey, give me the element in the position 0 plus 1. As you can see, I'm giving the position relative to the original position, the position 1, right here, right? So if you want to go back and you say, oh, list of 0 minus 1, what you are doing is basically going all the way around and picking the number 3. Therefore, in your list, your index 0 minus 1 or minus 1 is going to be equal to 3, which in reality is the index 2. These are both the same. Okay, as your list gets longer or you update it, you can keep adding elements to it. However, this one right here is gonna get updated as well. Whereas this one, well, it's also gonna be turned into 4. Okay, so basically this one always refers to the very last element in your list. So in other words, it's like if you had picked your list, taking it out, and then join the corners, you know, to form a circle. So this works when your index is going backwards, saying -1. But when you are in index in this last index right here, which would be 0, 1, 2, 3, in index 3, if you say 3 plus 1, you're going to get an error because there is no such thing, you know, as the circularity doesn't apply all the way around. You're simply going to get an error that is called error index out of range. Okay, so that's basically what is going on. So here is a visual representation of this problem. So we're going to have a sheet. We're going to have some sort of like a piece of paper that is going to represent our board. You can see the cells in there. So what we do is to just fold it so that the corners just join together, right? So they fold so that the neighbors that are at the top become, so the cells that are at the top have as neighbors those cells that are at the bottom of the grid. And you can take it one extra step to make it an object called a torus. It's a geometrical polygon, a three-dimensional polygon, right? That looks like a donut, where you can see that also these edges right here are gonna join together. So this visual representation is basically how our world is gonna look like. You can make it, of course, as complicated as you want, because once you have the torus, you can turn it into any sort of shape that you might desire. So this is always also Conway's game of life, but it's increased a level of not dimensionality because it's still three-dimensional, but the same principles apply. Notice how, you know, all the neighbors have a neighbors surrounding them, right? And it's because we join them, as in the GIF that I showed you previously. They form some sort of like a very convoluted torus. So that is what we are going to do. And luckily for us, it's very easy to represent. Okay, these states are easy to represent. It's not to graph like this, it's very complicated, but it's easy to represent as indexes when you are working with 2 dimensions. Okay, so let's start first with our Kahoot so that we can get a quick recap of the information that we saw on the last class. And I'm going to share this in a minute. If anybody has any questions, please let me know before we can actually start the game. Okay, does anybody have any questions or any comments? Okay, thank you, Joshua. Excellent. So I'm going to share the link now. There we go. And so you can simply click on it and you're going to join in. Or if you want to join with a different device, just go to kahoot.it and enter the pin. I'm going to get me a glass of water. Be right back. Oh, my screen crashed. No problem. We'll wait for you. Thank you, Justin. Or try also to join in your phone. But unless, of course, you can't see anything. It's in a corner of the screen and it's too small to read. Okay. Would it help if I read the answers to you? Okay. Yeah, something that I like about you guys is that you're quite tech savvy. So you usually troubleshoot very efficiently. Yeah, of course. Stop sharing. I just see Joshua's avatar right now. It's very funny. Naruto. I did. I definitely did. Yes. Yeah. Naruto Uzumaki. The one I didn't really follow afterwards was the one with the sun. Um, I didn't want the I didn't watch the sequel. Yes, Boruto. Yeah, that's the one. Oh, okay. Well, that's good to know. Yeah, I saw one episode when Naruto went back in time and met his Boruto went back in time and met his dad. That's very cute. Okay, so Justin, how are we doing? In the worst case scenario, we can delay our Kahoot and then have it at the end of the class if you want to do it, or we could just skip it altogether. And the reason why is because, well, there's only Joshua in the room right now. We should get more students. Oh, there we go. Okay, so I'm going to try to share my screen once more. Okay, excellent. I'm glad to hear that. So I'm going to share my screen once more, and then I'm going to copy and paste the link again. There we go. Awesome. All right. So we're all in. So let's start. 3, 2, 1. Off we go. Let's do this. Okay, there are some interesting questions here. Question number 1. Double the points. What does screen 0 represent in our data definition of X? You have our data definitions. Excellent. So the correct answer is the width. Okay, so what else? What other answers? The height. Yeah, you're close. Whoever picked the height, you're very close. So remember, a screen is a tuple, which means that it is something that contains two values. The first one with index 0 is the width. The second one is the height. Okay, we're going to need that definition in a bit. Alrighty. Second question, true or false? Our state data definition could be represented as a Boolean. Correct. That is absolutely correct. Now, in the simplest version of the game of life, that is true, right? Which is, it's only two states. Are you alive or are you dead? Excellent. Question number 3. Why don't we use a Boolean as primitive for our data definition state? Why don't we use a Boolean as a primitive for our data definition state? So the correct answer is because we need to count the states of all the neighbors. Okay, and we'll see this in a little bit. We talked a little bit about this last time, but so when you count Booleans, so keep in mind that each of your neighbors is going to have either a true or a false. So counting true and falses is a little trickier, requires one extra step. It's not really that hard, but it requires an extra step. If you pick numbers from the beginning, then you just need to apply sum to a list, and that's it. Okay, so that is why we are picking zeros and ones instead of Booleans. Question number 3, or next question, double the points. What does the helper function make alive do? Here you have a function that is called make alive. Look at the signature. You guys are rushing through this. So the correct answer is randomly make some cells alive. So you can see it. You can see it here. So basically, you are passing. You're going to pass a cell, and based on a probability that goes from 0 to 100, it's going to say, okay, you're alive. If you are less than the chance of being alive, then you are alive. Okay? Otherwise, you are dead. So the whole point is that you would prefer to have around 60% of your cells being alive at most. You know, if you go beyond that, then you kill everything. So it's not a good idea. All right. So next question. In this representation of the game of life, how many colors do you see? How many colors are in this representation of the game of life? All right, excellent. So there are 4 colors, right? The obvious ones plus black. So there you have green for those that seem to be sitting there doing nothing. And then you have red for other ones, and then you have white, and finally those that are dead are represented in black. All right, good. That was a tricky question. Let's build on that one. When do we not use a random module? We imported a random module. When calculating the chance of a cell being alive or dead. Okay, excellent. Yes, when rendering the animation. I'm impressed. I'm really impressed. Yeah, so when rendering the animation, so at that point, you don't need to randomize anything. You just need to call the current states. Oh, excellent. Next question, true or false? We use the random module once in the whole animation, and then we don't use it again. True. Excellent. Yeah, just for the initial board, and then we let the rules apply the rest of the game. What does the constant cell size do? What does the constant cell size do? Correct, all of the above. So it changes the number of cells that will be rendered, determines the size of each square in the grid, and finally determines how far apart 2 cells are from each other. Double the points. In a 3D game of life board, how many neighbors will each cell have? Good. It's starting to escalate. Third dimension. 26 is correct. Wow, look at that. Okay, next question. Double the points. Chances to flip the thing around. In a 4D game of life board, how many neighbors will each cell have? Did someone pick well? No, nobody picked well. So the correct answer is 3, right? 3 sides. Sorry, 3 in the left to right direction, 3 in the up to down direction, 3 on the back to front direction, and 3 in one additional direction, right? That's the point of being 4-dimensional. So in a hypercube, you're going to have 3 by 3 by 3 by 3 minus 1, which is only 1 cell. So what I want to show you with this is that no matter how many dimensions you escalate your game, there is always going to be 1 cell that you are talking about. All of the other ones are immediate neighbors. What determines the amount of time our animation will run? Excellent. A while loop. Good game. A fast game, but very efficient. All right, excellent. Good job. So that was our Kahoot, and we just passed our introduction. So let's start our live session. So today is going to be interesting because it's going to escalate very, very quickly because of the data definitions that we already put in place. So I'm going to share the link to the live session. Please meet me there, and we can start playing with the game of life. Okay, so here we are. So the first thing that you can see is that we have all the definitions that we made last time. Okay, so I'm just going to go through them very quickly to summarize. The first thing that we need to notice is the modules, what modules we need. We're going to need pygame to render the game and apply the rules in the grid. And the second one is random, which we already discussed in the Kahoot. The second thing I wanted to notice is our constants. We're going to increase the number of constants. At the beginning of your programs, you don't always need to know where everything goes. Okay, but it's good to know what are the most important pieces are. So we know that the screen is going to be essential, defines how big our game is. The cell size defines how many cells we can allocate. And finally, the chances of being alive is something that we created on the go. From there, those are our constants. We're done with constants. Let's start talking about variables. And the first one that we defined was X position. The X position, we defined it with our examples to be in a range of values that goes from 0 to the cell size multiplied by the number of cells that we can fit in our grid, okay, in a row. That's what this number means. So by dividing a screen of 0, which is the width, by the cell size, we get how many squares we can fit in a row. Okay, and then we multiply that by the cell size to get it in pixels. Then we apply the same thing to the Y direction. And in this case, however, the only thing that we are doing differently is that we are applying a screen of 1, is the second element, which is the height. Okay, but everything else is the same. It also goes from 0 all the way to a screen to the height divided by cell size multiplied by cell size. The third thing that our cell is going to have is going to be a state. It's going to be alive or dead, just like we discussed in the Kahoot. Then we use these 3 data definitions, which are primitives, to create a new compound definition that includes an X position, Y position, and a state. And we can see the examples right here. So we used a 3x3 matrix as an example, and then we automated the process, right? So to create a cell row. So you can see the cell rows, which is the next level in our data definition. So this is the point when we can get a little confused. So the cell is a compound object itself, an individual, an entity that is alive or dead, but it has those 3 elements. It exists in the space and it is alive or dead. So everything comes together. Wherever the cell goes, all those 3 properties go with that. Okay, and then we place those cells inside of a grid. We start placing those cells inside of a grid, but instead of just putting them in a 2-dimensional matrix right away, we analyze and think, hey, the first thing that you need to fit is the row. And then you fit rows all the way down till you finish the size of your grid. Okay, so here we are defining how many cells we can fit in a row. In these 3 simple data definitions, we are simply allocating three different cells. But in the CLR3, which is the last example, we are automating the process by saying, hey, create a whole row of individuals, of cells, separated by, this distance in the X position. And then give all of them the same position in the Y direction, because this is a row. Otherwise, you would be jumping around the matrix, right? If it is a row, it means that everything is aligned together in the Y direction, up to down. So, and finally, make them all be dead for now. And then, just reiterate as many times as you can fit in the screen. That's what CLR3 does. And then we define our cell grid. And in order to do that, we are in line 66 right now. We are gonna basically do the same thing that we did with the rows, but applied to the grid. In other words, we're gonna start accumulating rows until we fill the grid. Okay, so we see the simplest example here. We define three rows. Someone added more. Please erase that because it's gonna be hard to debug that later. Someone copied and pasted that. Okay, I'm gonna erase it. So this is gonna be a matrix of 3x3, CG0. And then we created a helper function right here that assigns a particular position in the Y direction. Okay, so it's simply gonna iterate over the different rows that we can create until we finish making them all. At the end, CG1 is gonna represent the first version of our grid. But we are not happy with that yet, because all of these cells are dead. We need to randomly make some of these cells alive. Which ones we don't know, but we know that there is a probability that each cell is gonna be alive. So we created a constant value that is called chance alive. that is going to go from 0 to 100. If it is 20, that represents 20% chance of being alive. And this is the point where we use a random module only once. We use rand int, which gives you a value that goes from the lower range to the upper value of the range. In this case, 0 to 100. Okay, if that probability is less than the chance of being alive, then make the cell alive and return that cell. We use this helper function inside of this list comprehension right here in line 91, and we end up with the grid that we are actually going to be using. So this, you can see how we started building from the simplest case, simplest data definition to the more complex one. So this is the fun part. We are done with the kind of like the hard part. So let's start working together on the animation process. Okay, so how do we start? I want to show you something interesting. So I'm going to refer, so from this line below, everything below is the main code. So I'm going to define a variable called CG that stands for cell grid. And I'm going to pick one of my examples. I could pick CG0, I could pick CG1, or I could pick CG2. Because I know that the only one that contains alive cells is CG2, I'm going to use that one. So I'm going to put a while true statement, a while true loop, so that my program runs forever. Okay. And inside, what should I do? Well, I need basically two steps. I need something that renders the game, and I need something that updates the game. So I wish, I don't have anything yet, but I wish that it had a function that does that for me. So the first one I'm going to call render. The second one I'm going to call update or step. This is more straightforward, a step. Now the render part doesn't take any arguments, and I'm going to show you why. And the step one does take an argument, which is going to be your cell grid, because it's going to have to update it, right? You need to give it something to update, and it retrieves you something that is updated. And that something is going to be also a grid, a cell grid. So notice how the value of CG gets updated over time, okay? And it's going to be fed to render. Actually, you know what? I was wrong. Render does need an argument that is CG as well. But contrary to the step part, it doesn't retrieve anything. Okay, it returns none. So let's define these functions. Let's start with the render part. Render CG. Let's start right above. Let's start with our function definition. Function definition render. Okay, what's the signature? Signature, what goes in? Well, it's going to be the cell grid. What comes out of it? Nothing comes out of it, because the job of this function is just to show you something in the screen, not affecting the cell grid, right? That's why we're not returning anything. So the purpose of this is to simply render the game. So let's create it. Render, and then it's going to take the cell grid. So what should we do now? Okay, the first thing that I want to do is to make a screen gray. Okay, every time that I run this, I want the screen to be rendered gray. Otherwise, I'm going to start putting things on top of other images. I don't want that to happen. So before I do this, at this point, I'm going to need pygame. Okay, I'm going to need one of the methods and attributes that pygame has. So I'm going to need to import the necessary elements from pygame to this game. So I'm going to go all the way up, and then I'm going to create a set of variables. I'm going to call it variables secondary to the main project scope, but necessary for pygame to run. Okay, and at this point, this is very straightforward, because it's like kind of like just getting the manual out, the manual for pygame, and putting it, in here. So there is no really analysis. If someone knows how to, please import the display into pygame. I'm gonna import the clock. So I'm just gonna call it clock, and it's gonna be equals to pygame.timer. I think it's timer.clock. Okay, so those are gonna be, I believe, the two things that we need to import. There's a third one that is called pygame.init. So here we're just calling, and I'm going to write it here. We are just calling a series of necessary preloads that pygame might use. And this is important that we specify that it might use them, because the program is going to run even if we don't put it there, but sometimes it creates bugs if we don't add it. So that's why it's important. Excellent. So excellent job on line 16. So we have pygame don't display. So this is a method from the pygame class, and display is a function itself. And we are going to call one particular method that is called set mode. Oops. Display dot set mode. Okay, and we are going to pass the screen. It's going to have a tuple, right? This is equal to saying 820 by 640. It's a tuple. It's an object that has two elements. Now, at this point, it probably also makes sense that I define what color I want my cells to have, right? So if my cell is alive, let's define a variable color alive, and let's give it a value of white in the RGB format. So it's just going to be 3 integer values. Someone help me with that. It's going to be a tuple that is going to have integer, integer, integer. Give me the white color. And someone else give me the color when the cell is dead. Okay, it's also going to be in a tuple. Go for it. So what's the maximum value that, you know, an RGB format can take? Excellent. There you go. Great. I'm super proud of you guys. Okay. So a small caveat here. So 000 is actually black. So we're going to represent that as dead color. Okay. And the other one that disappeared just now, oops, Chancellor color alive, that's going to be the one that is 255. There you go. Excellent. Now, we have only 2 colors for now, but keep your mind open that we might add more colors later. Okay, so let's go down to our render function at line 108 at the very bottom. There you go. Okay, so now what should we do? Okay, so I want to call display, and I want you to fill the screen with a color. What color is it going to be? Well, it's going to be the color dead. So someone fill it in there, please. So it's going to be the color when nothing exciting is going on, right? What should we do next? Now, because of how our data definition works, the cell grid, we need to start unpacking stuff. Okay, we need to start unpacking. And what I mean by this is that I'm going to iterate using a for loop, because this is a 2-dimensional loop. I'm going to need to run 2 for loops, one nested inside of the other. It's going to look something like this. For CLR, which stands for cell row in the cell grid, for cell in cell row. Now we're going to start rendering, you know, the images, the shapes. And, you know, we have 2 options in Pygame, really. Probably have more, but I don't know them. One of them is to import a sprite, import an image, okay, and place it in there. I'm gonna let it to you if you want to do it. The other one is to draw something from scratch, is to draw a rectangle. Okay, so I like where you're going with that. You're gonna draw a rectangle. So it's gonna be pygame.rect, pygame.draw.rect. Yeah, it's pygame.draw.rect. So it's gonna be a method in the Pygame. There you go. Excellent. And inside, we're going to have first to specify what surface we want this to be rendered in, which is display. The second thing that we need to specify is going to be the color of, you know, of this cell. Now, here is the first time that we encounter a dilemma. So we know that our cell is going to have one of 2 states. We don't know which one though. It's going to be alive or it's going to be dead. And the information is contained in this particular key, which is called the state. Okay, so if it is 1, it's alive. If it is 0, it's dead, but that's not a color. We need to transform this. And to do that, we're going to create a helper function that is going to use this as a wrapper. wrapper means that you make a sandwich out of it, right? To make it like you embed it, like fold it on top of something else that makes the transformation. So this one is going to be a color cell, for example. Okay, so now notice that I don't have this function yet. I'm going to need to define it eventually, not right now. Okay, so let's keep moving. After that, I need to specify now the shape that I want to make. And the shape that I want to make, I'm going to put it down here. Just so that it's more readable. There we go. It's not very Pythonic, but it's easy to see. So sometimes it is a good idea. It's going to be simply pygame.rect with a capital R. And this one is going to contain 4 elements: the position in X, the position in Y, and the size on X and the size in Y. If someone can do me the honors, the first one is contained within the cell. It's called the cell in X. Someone can update the value. That'd be great. If someone can pass that argument, that'd be great. Notice how I call the cell state using the key. So now the X value is going to be embedded within the cell. What key contains the X position? So you know that you're going to need to call cell, right? And probably you're going to need to pick one of the different keys that you have. You have an X value, a Y value, a state, and I think that's all we put in our cell. Yeah. So we need to specify X. There we go. So that's it. So we're specifying X, then we need to specify Y. Someone do that for me, please. And finally, we need to specify how big you want your rectangle to be. That is going to be equal to cell size for X and cell size for Y. There you go. And what else do we need to do? Well, at this point, we're done with drawing the different cells. Okay, it's going to draw all the cells for each row, all the cells for each cell. However, I see someone click the wrong button. Good. Before we can render it, before we can see it, we need to call an additional argument that Pygame needs. That is called pygame.display. Now, don't confuse this display with the variable that we just named. It's a different thing, and we're gonna call flip. Okay, and finally, we're gonna call our clock thick. I think it's called, and then we can specify the speed of our animation. Now, animation speed can go from 0 to a really big value, okay? If it is, the lower it is, the slower your animation. Sometimes 15 is a good idea. We can try with 60, because this is something that would be nice to change from the top of our program. We're gonna put it in a constant. Notice that this value is not affected by our program. It doesn't get updated, it doesn't change. So let's call it animation speed. Okay, and let's create a new variable, a new constant, sorry. Animation speed is going to be equal to 60, someone say. Okay, now if you want, run it and let's see what happens. Let's run the program, let's see what happens. Errors, probably, there's always something. Yeah, there it is. Pygame has no attribute timer. Where is it? Let me see, pygame.timer.clock. I think it might have been capital. Let me check. Oh, it's just time. It's not timer, it's just time. Okay, someone run it again. Oh, color cell is not defined. We forgot to define our helper function, of course. Okay, so we are back in render, in the render function. Let's create a helper function right above it. So function definition, color cell. So if someone knows, can you please fill the signature? Signature. What goes in there? What comes out of it? And I see someone already working in the function. Go for it. Go for it. Don't wait for me. Just if you know what you're doing, go for it. Whenever you know, it's good to explore. I really encourage that. Okay, while you guys do that, I'm gonna help with the signature. And what goes in there, you know, we have two options. We can pass the cell itself, or we can just pass the state. I'm gonna pass the cell, you're right. I'm gonna pass the cell function, the cell data definition, which is a compound object. And what comes out of it is simply going to be as a tuple with 3 values. Okay. And this tuple represents one of the colors a cell can have. Okay. We have those in constants. So we'll refer to those ones. Okay. So let's start our function definition. And in this case, what we need to pass is simply cell. So what should we do? So basically we need to evaluate, A, if your cell is alive, then return the color alive, else return color dead. That's what we need to do. Excellent. Yeah, go for it. Take your time. There is no rush. Excellent. So let me check. Okay. Good. So the core concept is there. So the core concept is there. Now I'm going to show you how to make your code pretty in terms of functionality. So if cell at the state, so a state currently doesn't exist as a variable. So we need to call it in the context of the cell. There you go. Excellent. So you need to, excellent. Good. Correct. So it is a key. Otherwise, good. So the second expression, alive. So there is nothing that is really called alive, but there is something that is very similar. That is STA, which stands for a state alive. If you go back to your definitions, when you define the state, you created 2 examples: STA for alive and STD for for dead. Okay. Additionally, because this is just binary, you can name the cases raw. You can just say, hey, if this is 1, that means it's alive. If it is 0, that means it's dead. So you can do both, right? There's been an error in reality. There you go. Yeah. Excellent. So those are the only 2 cases. Now let's work in that pass. So in the first case scenario, what should we do? So if this cell is alive, I want you to return something. That something is going to be a tuple with the color that represents the alive cell. We have a constant for that. What constant is it? Let's put it in here. There is a constant there that gives us a tuple representing the color white, right? So we just need to pass that one right. Excellent. And if it is dead, well, give me the color dead, which is called black. Okay, so the name of our variable is color white. And the same for the other one. Excellent. Okay, so there is really no else case. Everything that is handled as an exception from these 2 rules should be considered dead, right? Otherwise, we would break the program. Because imagine, if you want to return this is not even a tuple. This is not even integer, right? It's just a string. So we need to handle it properly. These 2 clauses, we're going to get rid of. Remember, when programming, getting rid of stuff without reducing functionality is a good thing. And simply return color black, I think it was. Let me check. So, oh, color dead and color alive. So it's not white, it was my bad. It's alive and it is dead. Okay, but remember, there is no else. Here is the fun thing. There is no else. Because look, if this cell state is alive, then it returns something. Anything else must be dead, right? So there is no else. So if this if statement doesn't hold, then the other alternative is the one that is passed as a return value, right? So that's why we don't use an else statement. So it's a very concise way to create an if statement. Okay. So now we have a color. Let's run it and see what happens. Says it's thinking. Sometimes you need to run it a couple of times. Yeah, this laggy behavior is not because of our program syntaxes. It's just an error with Replit. Let me refresh the screen. Oh, something's going on. Let me refresh. Give me 1 second. There we go. Okay. If you guys can see the same as I'm looking at, now we have a grid, you know, with some squares, some white squares randomly placed around it. Nothing else is happening, but we have the grid. That's great. That's great news. Now we just need to animate it. Okay, so the part that has to do with graphics, we're over it. We don't worry about it. Now, that means we're gonna think modular in a modular way. We're gonna separate the graphic part from the update part. So let's work on the next data definition. Someone is writing, I love it. What's going on? Animation, yes, and let's put render down there, just for the sake of it. I like how you're thinking. Okay, so now there is an important consideration as well. What goes first, the updating step or the animation? The clue is given by the value that we give in the cell grid. Notice that we already gave the initial state, right? The cell grid at the initial state has its cells, some alive, some dead, okay, but it's ready. It's ready to be animated. It's ready to be rendered. So the first thing that we're gonna call is render. After that, we're gonna call the steps, update steps. Okay, that's gonna be this one right here. So notice one thing. I am returning something from the step that is the same thing that I am feeding to that function, which is cell grid. I'm giving cell grid, I'm updating it, and I'm receiving it back. Okay, so that the render can update, can render that updated cell grid. So let's start working on the step, and this is going to be the fun part. So function definition step, signature enters cell grid, exits cell grid. The purpose of this is to simply update the cell states based on game of life rules. So, you know, at this point, it might be smart to say, what are those rules? Let's type it as a comment. So let's start here. And we know that we need to feed a CG, which is a cell grid. So let's define the three different cases, three cases. The first one is if cell has 2 or 3 neighbors, then make it alive. If cell is dead, actually, let me update that. If cell is alive and has 2 or 3 neighbors, becomes alive in the next generation. If the cell is dead and has three neighbors, exactly three neighbors, then make it alive as well. Everything else, dead, okay? If you were dead, you stay dead. If you have too many or too few neighbors, you are dead as well. Those are the rules. Now, I'm gonna put them down below. So what do I need to do? Because of the structure of the cell grid, you know that you're gonna need to process each cell independently. And in order to access those cells, you're gonna need to unpack. You're gonna need to extract the information. The way we do it is by saying, again, for cell row in CG, that's the first for loop, we're gonna include a second for loop for each cell in the cell row and something, right? As you said before, pass. So what should we do? Okay, so at this point, we need to count how many neighbors you have. So if you are D cell, I'm gonna count 8 neighbors based on the index that you have. Okay, so index 0 is gonna be the position of this cell. Index -1 is gonna be the position at the previous row if you are counting CLR. And it's gonna be the neighbor to the left if you are counting the previous index in the cell parameter. Let me show you what I mean with this. I'm gonna change the way we create these for loops. Actually, before that, I would like to, so right now you agree that this cell contains 3 elements, contains X position, Y position, and then the state. We don't need all of this. We just need the state. So I would love to have something that extracts, give me an exact copy of the cell distributions, but only in terms of their states. In other words, I'm going to extract all the states from all the cells and then count them as one single thing. So I'm going to do that with a list comprehension. So I'm going to show you how to do very fancy list comprehensions. So here I'm just going to call the cell and I want the state. And I'm going to place this into a variable. With these comprehensions, the expression, the statement, sorry, what goes inside gets cut, placed to the left of the immediate for loop that preceded it. And then we erase those semicolons. This expression right here means pick all of the states for each of the cells in the cell row. We're going to cut this and we're going to paste it on the left again. Now this means for each row, for each cell, extract the cell state. Okay, so notice what we did. So we created the standard nomenclature for the for loops like this. And from there, we started creating our list comprehensions. And the reason why we need a list comprehensions here is because we can create only one single variable that we can call states. Okay, we can call it STS. And I would normally give a more straightforward name, but I name it STS because I need something that is short. You'll see why in a minute. Okay, so now this contains an exact copy of each cell relative to their states only. So it's gonna be only zeros and ones. We're gonna iterate over the different cells now. Let's create it again. Let's unpack our cell grid. For CLR in CG, someone do me the honors with the cell. For each cell in CLR. Oh, sorry, no, not running it yet. I would throw an error. Okay, so for cell in CLR, now we're gonna start counting the neighbors. So neighbor is gonna be equal to 8 different cases. So here they are. So the first thing that I'm going to do is to call the states. States at the position, the previous position from the cell row. So currently, I don't have reference to an index. I'm just passing the object. So I'm going to change this to a number. This CLR will refer to a number, or better yet, we can call enumerate. So it's going to be index CLR, comma CLR in enumerate CG. What this means is that it's going to pass me the index of the object, and I can decide what to do with those. Okay, but it is the index, the number that I can use, the position of the CLR in its list that I can use to refer to the previous and the posterior neighbors. Same goes with the cell. So I'm going to call index of the cell, comma cell, in enumerate CLR. Okay, so now pay very close attention to what I'm going to do now, because this it can turn very confusing. It's going to be a lot of words. So I'm going to refer to SDS at the index. I'm going to write a comment here. So this is the distribution of our cells. XXX, XXX, where the cell of interest is this one right here. Okay, the one in the center. Everything that is before that cell is in index I CLR -1. Everything here in the same row as the cell of interest is in index I CLR, and that's it. And the third one, what you can imagine, is going to be +1. Okay, so those are going to be the 3 different indexes based on rows. Now let's define those neighbors. Thank you. Yeah, it was bugging me too. Okay, neighbors is going to be equal to a list of items. SDS at index of CLR -1. Right? I'm working with these 3 first. Everything is going to look like this: SDS of I CLR -1, like that, comma. Then the next one, which is here. So this one is going to be equal to SDS of I of CLR, and that's it, without the -1, right? Because it is the second row, is this row right here. So there is no -1, that is the row of that at which we are working. And the third one is going to be +1. I have a comment here. Justin is about to say something. Okay, so while we wait for Justin, does -2 or 4 work? It does, but then you wouldn't be considering the immediate neighbor. You would be considering 2 neighbors to the left or 2 neighbors to the right. You know what? That would be interesting. Once we're done with this animation, let's go back to that and see what happens. I never tried it. Must be something interesting. Okay, so good question. Good question, Justin. So here we have the 3 rows. The first row, the second row, and the third row. Now notice that because we are working with a 2-dimensional matrix, we need to also specify a particular column. In other words, besides these, each of these open and close square brackets, we need to add a second one that refers to the particular position in that row. So the first one to the left is going to be -1. So it's going to be equal to the index of the cell -1. And all of the elements on their left are going to have the same value. Those in the center are going to have simply index of cell without the CL, without the -1 or +1, just like that. And finally, the ones on the very right are going to have, let me minimize this. There we go. The ones on the very right are going to have +1. So pretty straightforward. For the computer, for us, not so much. It gets confusing. Okay, there we go. So technically, these are the neighbors that we have, except for 2 problems. The first one, this item in the center that I'm pointing at right now, I highlighted, is the cell of interest. So we shouldn't count it as, you know, as the total number of neighbors, right? Because if it is alive and I have 3 neighbors, by adding this cell that is alive, I change it to 4, and therefore I kill the cell, something that shouldn't happen because it has 3 neighbors. So I'm gonna get rid of this one in the center and replace it by a 0. Okay, that's the same as just getting rid of it, except I respect the dimensionality of my grid. Okay, so there we go. So what have the neighbors? So we're gonna have to update that neighbor value by simply saying sum of neighbors. Now you can see why I didn't use states with a Boolean, because if this had been true or false, it would have taken some extra steps to just, count them as zeros and ones and then summing them. Okay, so that's why we use zeros and ones. There we go. Now that we have the neighbors and the values of the neighbors, we can start applying the rules. So let's go back to those rules. I put it somewhere. There we go. So 3 cases, and let's put it inside of the loop. If cell is alive and has exactly 2 neighbors, then keep it alive. So let's code that. If cell state equals 1, column, if neighbors equals to 2 or neighbors equals to 3, right? So I already made the sum. So I have the total at hand, it's a number. Then what should I do? Well, the cell state is going to stay alive. So it's going to be equal to 1. Otherwise, and here we do use the else case because we need to handle those exceptions, it's going to be equal to 0. What else happens? Well, if it is not alive, it's dead. If the total number of neighbors equals 3, that means that you survive or you are born in the next state. And therefore you become alive. Everything else dies. So it's going to be state equals to 0. There we go. And those are these cases right here. So if cell is dead and 3 neighbors, alive. Everything else is dead, right? This one right here. And this one, I guess, goes here. Before we run it, we need to return something. Remember, look at your signature. You are supposed to return cell grid updated. Thank you so much. Cell grid updated. Okay, so let's simply add it. So someone please add this statement, just a return clause with the updated grid. So we just call return, right? Return CG. So let's run it and see what happens. Well, we started. Oh, someone modified the import statement. No problem. There you go. What else? Oh, almost. What does it say? Ah, that's the second error. Index out of range. We're getting this error because we are trying to refer to the neighbor of one of the right corners or one of the down corners. Okay, as we defined it before, you need to decide what to do with the corners. So we're gonna kind of like, like make this like a circular world where the neighbors from the very beginning are the neighbors from the ones on the very edge to the opposite direction. So there is a very neat trick that you're gonna use, hopefully a lot. So follow me in line 138. You're gonna love this one. So here, I'm gonna, so 2 things. The first thing is I'm gonna select everything that I'm gonna modify, and then I'm gonna press Control D. Everything that looks the same is gonna get selected. Control D in Replit, and also VS Code. Other editors, might apply different ways, but VS Code and Replit accept this command. So first, I'm gonna wrap this in a parenthesis, not because it's gonna be a tuple, but simply because I'm gonna apply an equation, an expression. So I'm gonna divide this by a modulo. Modulo is basically calculating the remainder. When the value is other than whatever you are using the modulo against, it's gonna give you the original value. But at the moment that that modulo hits or that expression is the same, both values are the same, then it gives you 0. Therefore, you're going to be referring to the value at the 0 position in your list. This is what I mean. So I'm going to say length of CLR, of cell row. Okay, so notice how I put it only on the elements at the very right, the last elements. This one, and this one. The other ones don't need it. The other ones don't need it at all, right? Because they always have neighbors to the right, except for these ones that are already on the right. Now, in the same analysis, in the same token, something similar happens to the opposite index, the index of the rows. This one, and this one. You see, they're all at the very bottom. So we need to do the same. So I'm going to press Control D, Control D, Control D, wrap it in a parenthesis. Oops, you know what? We need to include the plus one. There we go. Wrap it in a parenthesis and divide by modulo. So this time is going to be the length of CG. Now, see how I wanted you to pay attention to this? It's because it's very easy to get lost. Look at all these things that are going on. So if you're not systematic with that, you're gonna do what I did and you're gonna get completely lost and you're gonna need to do it again. Anyway, so now we are not getting any errors. What is going on here? So we have our grid, and now well, our grid should be updated, right? So we're not getting any errors. So what is going on here? Oh, okay. So we need to add one indentation here. Hopefully that solves the problem. There we go. And there is our Conway's Game of Life. Now, I don't know where these little guys went, but someone please change the, oh, there we go. Look at that. So the animation speed was set to 60. That's really fast. So I'm going to change it to 20 so that it's easier to see. Let's see what happens. Look at that. There is more behavior now. But now, you know, the squares are too big. So let's reduce the size from 50 to, let's say, 12. And if everything goes well, then we have a really nice looking, you know, grid with the Game of Life in it. Okay, so that was, that is the end of this exercise, pretty much. It's a functional Game of Life grid. So notice how we're just using 2 steps and they create this complex pattern. Now, notice that in the Game of Life, there are different types of organisms, right? You have some that, you know, migrate. Once all the commotion, all the motion settles down, you can see some that, you know, migrate, some that are static, some that don't move at all, etc. Okay, so that is what Conway's principle was. It's a series of very simple rules create very complex patterns. Now something weird is going on there. Someone moved something. Oh, that's what's going on. Someone's messing with my head there. Someone already changed the indexes. Okay, so that's what happens. That's what happens when you change the indexes. You break the system. Okay, not all errors are runtime errors, which means that not all errors in your program can be retrieved with Python. Sometimes your program runs, but it runs in a weird way. Okay, so now you know what you need to use -1 instead of -4. So I'm going to show you something really cool. But before I do that, so what I'm going to show you is how to color, how to add additional colors to the Game of Life. But before that, does anybody have any questions? Okay, Justin says I'm good. Okay, so let's bring this back to the functional version of the Game of Life. Thank you. Yeah, thank you so much. There is one more there, so let's just run it again and see what happens. Oh, there's another 4 too. Oh, syntax error. Oh, there is a missing square bracket there. Okay, good. So let's think about our data analysis. So at the very top, we have our data definitions. We're not going to mess with the structure of the grid, but it would be cool if instead of having to define a helper function when we render something, we instead allocated the color of the cell in a new data definition that we can simply update wherever we want, probably in the step, in the step function. Okay, so let's do that. So I'm going to go all the way up to before I define the cell, because the cell is going to have that new data definition. And right before cell, I'm going to create something called data def color. Okay, and I want to interpret this color. Well, color is just going to be color. There you go, color, followed by a modulo. So, and it's going to contain, what should it contain? Well, at least a tuple with 3 values, integers, right? The RGB format that we talked about. So I want you to interpret this as the color of a cell depending on its state. And I want you to think of the modulo as one of the following cases. Give me 1 second. 1, 2, 3. So A for alive. A for alive. D for dead. And B for born. That's going to be the new state. So let's create a new constant up there. Or you know what? Let's create it down there as well. So let's create the first example. Color lower score A equals 255 to 55 to 55. There you go. Color D, color dead equals 0, 0, 0. Color B equals, let's say, how about red? 255, 255, 0, and 0. That's going to be red. Okay, and so now let's add it to the data definition for cell. In a dictionary, we can call it color, and it's going to contain the color. So let's update all of this just for consistency. Otherwise, you could throw errors. Color is going to be equal to, let's say, color alive. Okay, all of these are alive. And we also need to update CLR3. Look, we are automatically creating the states. So we need to update it too as well. Color is going to be color dead, I believe. Yeah, color dead. Okay, and I think that's it for the data definitions. Now they are included in the grid. All of the cells now have an additional attribute. And it is, notice that even though we keep updating stuff, if you keep trying to run it, it still works. We haven't broken anything because we work systematically through the definitions. And if we want to add something new, we start with the primitive data types, which is in this case, the color, which I guess would be a compound, and then we add that to the more complex data definitions. So now we just need to specify what color to render. So I'm going to go to the render function, and instead of calling color cell, I'm simply going to call directly the cell with the color. Okay, that color is going to already be in an RPG format, so I don't need to do any extra step. The third thing that I'm going to do is going to be in the step function. In the rules, if I just survive, I don't need to change color from white. If I just died, I don't need to change color from black. But if I am born, I'm going to change the cell color to red. Color born. Okay, so let's run it again, and let's see what happens. Whoa. Well, that's not right. So here is what's going on. Oh my God. Okay, so here is what is going on. So I changed the color to red, but I also need to change it back whenever the organism is no longer born. So that's why we're looking at all those crazy that bloody image. So I'm gonna update it here. Give me 1 second. This is gonna be color alive. And this one is going to be cell color equals color dead. Okay, run it this time. This time it should run. There we go. Okay, much better. Now, the squares that are red are those cells that are born in this generation. If they survive to the next one, they turn white. Otherwise, they just stay red. Okay? So that is how easy you can change the behavior of your program if you work systematically. Now, let me tell you about homework. So please pay attention to my screen now, because this is something that you don't have access to yet. So actually, you know what? Let me just share it in the screen. So you're gonna click on this link in the chat, and then you're gonna fork it. Okay, so um, if you are logged into Replit, if you're logged into Replit, you're gonna be able to see something that looks, give me one second, that looks like this. All right, so at the top right edge, right side of the window, there is a blue button that says fork repo. So if you click in there and you are logged in, you're going to be able to import an exact copy of this project in your Replit account. So I want you to do that. And once you're done, please share the project with me so that I can give you some of the feedback. So here are the instructions. This is exactly what we just did in the live session, but this time you're going to need to do it yourself. Okay, so the instructions are there. Add color to the game of life. You can make it as complicated as you want it to be. You can create additional cases, like, for example, okay, what happens if the cell has been alive and survived for longer than 10 times, 10 generations? In that case, well, create an additional color, turn it into an additional color. Okay, so this is my game of life, the one that I've been using. Uh, give me one second, please. So what's our live session? Started answers. Here it is. So my game of life has 5 colors, the one that appear in the Kahoot, and those cells that are too old turn gray, but it's a paler gray than the one in the background. So if we are lucky, we're going to be able to see them. Here it is. So here is my animation. Look at that. So you can see that those squares that are older than certain threshold that I defined, turn into a paler gray. The dead cells are black. The cells that are just born are red, and the white ones are, survivors. Okay, so you can make it as complex as you want, but this is basically what we are aiming for. Alrighty, so I'm gonna stop share and I'm gonna stop the recording. If you guys want to